Welcome to this module, where we explore three vital elements of solar PV plant design: earthing, lightning protection systems, and proper marking and labeling. These are not just technical details. They are the foundation of safety, reliability, and compliance in every solar installation. In this session, you'll discover how effective grounding and protection systems safeguard people, equipment, and the environment, while proper marking and labeling ensure smooth operation and maintenance. Together, these practices enhance the performance, resilience, and longevity of solar PV systems, building a safer and more sustainable solar future. Earthing is the backbone of electrical safety in any solar PV system. Its main function is to provide a low-resistance path for fault current to safely flow into the ground, as the name suggests. This helps prevent electric shocks, fire hazards, and equipment damage. All metallic non-current carrying parts, such as module frames, inverter enclosures, and mounting structures, must be connected to the earthing network. This ensures that if any fault current leaks due to insulation failure, it is safely discharged into the earth without harming the equipment or personnel. Understanding earthing principles and choosing the appropriate system is critical to solar PV plant safety and performance. A correctly designed and maintained earthing setup ensures safe dissipation of fault currents, reduces electrical hazards, and contributes to long-term system reliability and compliance with industry standards. Different types of earthing are used in solar PV plants, depending on system capacity, soil resistivity, and available space as explained. Plate earthing involves burying a metal plate, copper or GI, vertically in the soil, suitable for small to medium installations. Provides reliable contact area and stable resistance. Rod earthing consists of one or more metal rods driven vertically into the soil, commonly used in medium-sized systems and rocky terrains. Simple, cost-effective, and easy to expand. Strip earthing uses flat strips of copper or galvanized iron buried horizontally in a trench to provide more contact area with the soil. Ideal for large solar farms, offering broad soil contact and reduced voltage gradients. Pipe earthing employs metal pipes acting as electrodes, helps maintain low resistance through moisture retention, uses hollow galvanized pipes that retain moisture for stable resistance, commonly used for inverter and equipment grounding. Chemical earthing uses a chemical mixture such as bentonite, graphite, or salt to improve soil conductivity and maintain consistently low resistance in dry conditions. Chemical earthing is ideal for areas with high soil resistivity, requiring minimal maintenance and ensuring stable resistance throughout the year. Suitable for high resistivity soil and large installations. Requires minimal maintenance and offers long-term stability. An effective earthing system should have low resistance, preferably below 1 ohm for large plants, and ensure quick dissipation of fault currents. Selecting the right earthing system in solar PV plants is vital to ensure electrical safety, protect equipment, and maintain consistent performance under varying environmental conditions. The selection depends on several key factors. Soil resistivity determines how easily electric current can flow through the ground. Moisture content and temperature affect the stability of earthing resistance over time. System type, whether grid-tied, off-grid, or hybrid systems, influence grounding configurations. Fault current capacity. Larger systems require earthing arrangements that can safely dissipate high fault currents. Maintenance requirements. Earthing pits must be accessible for periodic resistance testing and inspection. Procedure for selection includes performing a soil resistivity test using the Wenner or Schlumberger method, selecting the appropriate electrode material such as copper, galvanized iron, or chemical electrodes, designing the earthing grid layout, whether single-point, multi-point, or mesh type, testing and verifying that earth resistance values are within acceptable limits, usually 1 ohm for large-scale PV systems. A well-designed and rightly selected earthing system ensures that fault currents are quickly and safely discharged, reducing the risk of damage to equipment or electric shock. Lightning strikes are one of the biggest natural threats to solar PV plants. A lightning protection system, LPS, is designed to intercept lightning strikes and safely discharge them into the earth. The main parts of an LPS include the air termination system, lightning rod, down conductor, and earth termination network. There are 2 common design approaches. Angle protection method defines a protective angle, typically 45 degrees from the tip of the lightning rod. Rolling sphere method involves imagining a sphere rolling over the installation. Areas touched by the sphere need protection. This method is more accurate for large solar fields. Types of lightning protection systems. The main types of lightning protection systems are passive systems, like the traditional Franklin rod, and active systems, such as early streamer emission, I-SED terminals. Other methods include the meshed conductor method and the Faraday cage method, which create a network of conductors over a structure. Franklin rods, the conventional and oldest type of system. It uses a simple metal rod placed at the highest point to intercept lightning strikes and guide them to the ground through a conductor. Meshed method. This method involves a grid of conductors that cover the roof and sides of a building, creating multiple points of capture to protect against direct strikes. Faraday cage. This method uses a conductive mesh to enclose a structure, providing a complete protective cage. Early streamer emission. This newer technology uses an ionization system to create an upward electrical tracer that is emitted before the natural lightning strike, giving it a, quote, a privileged point of impact and capturing the lightning at a higher level to protect a larger area. System components. A complete lightning protection system also includes several essential components to work together. Air termination system collects the lightning strike. This can be a Franklin rod, I-SED terminal, or meshed conductors. Down conductors provide a low resistance path for the current to travel from the air termination system down to the ground. Earthing system safely dissipates the lightning current into the ground. Surge protection devices, SPDs, protect sensitive electronic equipment inside the structure from overvoltages that can occur even from indirect lightning strikes. Surge protection devices are installed at inverter and control panels to protect against voltage surges caused by indirect lightning and are categorized under internal protection systems. Marking and labeling are essential for safety, communication, and maintenance in PV plants. Labels indicate potential hazards, identify equipment, and guide technicians during maintenance. Examples include high voltage and danger warning signs, identification labels for cables, fuses, junction boxes, and inverters to identify hazards like electrical shock, earthing and isolation point markers, current direction arrows for AC/DC flow. Labels must be durable, visible, they must be permanently affixed, legible, and often feature a standard format with white text on a red background for visibility. Key labeling requirements. Location. Label all points where electrical work may be performed or where a hazard exists. This includes disconnects, AC and DC, junction boxes, combiner boxes, inverters, and other enclosures. Hazard identification. Label all PV power sources with photovoltaic power source and include warning labels for electrical shock hazards. Technical data. Include specific technical information such as maximum system voltage and circuit current, maximum power point voltage and current, AC output operating current and nominal voltage for inverters. Rapid shutdown. Label any rapid shutdown switches clearly, even if they are integrated into another component like the DC disconnect. Meter and utility connections. Label the primary utility meter to indicate a PV system is connected. Environmental resistance. Labels must be durable enough to withstand the elements where they are installed, such as UV exposure, rain, and wind. Visibility and legibility. Labels should be permanently affixed, legible, and visible after installation. Many codes require reflective properties and a minimum text size, such as 3/8, 9.5 millimeters tall, using white text on a red background. Labels should be weatherproof, UV resistant, and corrosion-free. Metal engraved tags are ideal for outdoor use, while printed plastic ferrules are suitable for indoor and control room wiring. Adhering to international and national standards ensures safety and performance compliance. Important standards include IEC 60364, Electrical Installation and Earthing Guidelines, IEC 62561 and AMP, IEC 62305, Lightning Protection Systems and Component Design, NEC, National Electrical Code, Regulations for Electrical Wiring and Grounding, IS 3043, Indian Standard for Earthing Practices. Compliance ensures that PV installations can safely manage fault currents, lightning surges, and labeling accuracy. Regular inspections and resistance tests should be performed to maintain certification and safety integrity. Proper earthing. Lightning protection and accurate marking are vital for the reliability and safety of solar PV systems. Together, they ensure personnel safety, protect valuable assets, and comply with global standards. A well-maintained protection system minimizes downtime and enhances long-term plant performance. Thanks for going through and reading. Don't forget to like, share, and subscribe for more solar insights from I-SED Academy. Please go to I-SED Academy platform for detailed learning about solar technologies.